Hi, welcome to this Omron Tech Talk. In the next 2 minutes we're going to talk about the importance of shielding in motor cables. Typically in most applications nowadays, a motor is driven by an inverter drive. In an inverter drive, the AC motor isn't actually being driven by a sine wave. To control the speed, the drive is actually pulsing the motor to simulate this. So essentially, AC comes into the variable frequency drive and it fires out a series of very fast pulses. We can vary these pulses both in the frequency and in the width to create this pseudo sine wave. Because a squirrel cage motor is just a dumb lump of metal, it sees the average and that's what gives us the AC waveform. It switches on and off very quickly through the use of what we call RGBT transistors. These transistors switch on and off very, very quickly. And in fact, the rate they turn on and off can range between 2 and 15 kilohertz. RGBTs themselves can actually pulse up to 100 kilohertz. And if we imagine a single pulse of 1 millisecond would equal to 1 kilohertz. One of the issues we have when we have high frequency pulsing is an issue called harmonics. Basically, any waveform consists of a base sine wave and harmonics in the first, third, fifth, seventh multiples of frequencies generated. These harmonics are basically the unwanted higher frequencies that are superimposed on the AC waveform, causing a distorted wave pattern. So we can see the base frequency here, and the first, third, fifth harmonics all build up to give us this interference that rides across the carrier wave. The problem with harmonics, though, is that these harmonics, they interact with the impedance of the power distribution circuit. So this can essentially cause voltage distortion for anything else connected to it, and any other loads. So it's not really a desirable thing. Now, we need to get rid of these harmonics, and we all know from basic physics that in a circuit, to have a current, you need to have a closed loop. But for the high frequency harmonics, this loop might not be the way you hope it to be. It could go through a comm circuit, or perhaps a sensor cable. How we mitigate this is the use of proper cable shielding. So typically, what we'd use is an inverter or motor-rated cable. In this situation, both ends of the cable are shielded and connected to ground, either through a motor ground here or a yoke close to the inverter cable itself. The contact should be a high-frequency, low-impedance path with as large an area as possible. This is to ensure that those harmonics go through the actual cable itself rather than through another circuit. So we can see here, we have our AC wave with the harmonics going to the motor, clean waveform coming back, and in this situation, our harmonic noise is returning to the inverter through the shielding. Typically, if we were to open the shielding up, we'll find there's two types. We have a high denier braid, which is essentially acting as a low DC resistance as the return path for the noise, and we have a mylar back foil. And the mylar back foil, with the glanding at both ends, helps to contain any noise. If you have a non-shielded cable, this can essentially act as an aerial and broadcast noise and radio frequencies into other circuits in the panel. So just to recap how we would mount an inverter, we'd mount the inverter on a metal backplate, a galvanic backplate within the cabinet, obviously use an EMC filter. We then have a clamping yoke, which you see here, as close as possible to the inverter, and then another EMC gland, which is grounded at the motor side. We then keep the cable as long as possible and try not to break it. So this is a very quick overview of the importance of shielding and using the correct glands in a motor cable. If you'd like to know more about Omron and our panel products, please visit the Omron panel website. Thank you.